Example 3 is a little bit more complicated than the first two. Here we have an object being thrown vertically downward from the top of a building 50 meters high with an initial velocity of 20 meters per second. What is the kinetic energy of the object just before it hits the ground? And it says ignore the effects of friction. Well, that's nice they tell us to ignore friction. But I'm going to draw a little diagram to try to illustrate the point here. And we're going to think about the energy at the various points along the way. So there's the top of my building. Now this object at the very beginning has an initial velocity equal to 20 meters per second. It also has a height above the surface of the earth, 50 meters. So at the very beginning, when you think about the energy, the total energy is going to have some kinetic, because it's traveling, plus some potential, because it's also above the surface of the earth. So the total energy at that point can be written in that form. We know the velocity and we know the height above the earth. So we've got both those answers to answer the question total energy. Think about it just before it hits the ground. Just before it hits the ground, it has some final velocity which will be greater than 20 meters per second. But think about its total energy. The total energy in this case would be all kinetic. There's no potential left because you're just before it hits the ground. So at the bottom, had we known the final velocity, it would be quite easy to solve this question. But since we don't know the final velocity, and we're not being asked to find the final velocity, we can't use that piece. What we're going to use is we know that total energy is constant. And we have to keep remembering that, because that's one way that they try to trick you on diploma exams. They'll give you a bunch of little pieces of information about the beginning, and then they'll say something with reference to the end, and all of a sudden you think, well, I don't have enough information to do that. Well, you do. You have the velocity at the beginning. You have the height above the earth at the beginning. You can use that first formula to find how much kinetic energy it has before it hits the ground. Because if you can find the total energy at point 1, probably easier to describe it that way, it'll be equal to the total energy at point 2, which will be equal to the kinetic energy at point 2. So the total energy at the top will be equal to all of the kinetic energy at the bottom. All of the energy is transformed into kinetic. That's why it's going faster, is because what potential it had became kinetic as well. So let's work this out. Energy total equals energy kinetic. We have a formula, 1/2 mv squared. And I'm going to use VI squared plus energy potential mgh. We know the velocity, we know the mass, we know the height. Let's substitute everything in. 1/2 times 4.0 kilograms times the initial velocity 20 meters per second squared plus 4.0 kilograms times 9.81 newtons per kilogram times 50 meters. Punch that in on your calculator. And again, I'm just going to punch it in to verify my answer. And you should get 2762, which when we go to the appropriate significant digits should be 2.8 times 10 to the 3 joules. So be careful. If you really understand those two diagrams, those examples, you'll look at that bar graph and notice that the total energy always kept a constant value. It was just always kinetic potential changing from one form to another, but the total was always the same. And when you looked at that pendulum at maximum displacement, when it was at its highest point, it was all potential. When it was at its lowest point, it was all kinetic. The roller coaster, the same thing. Highest point, all potential. Lowest point, all kinetic. But the total never changed.